Good afternoon, students. So today we are going to learn what is meant by Ehrenfest theorem. Okay. So actually, Ehrenfest theorem, it gives the correlation between classical mechanics and quantum mechanics. That means that actually we have to represent in quantum mechanics any particle motion as a wave packet. Okay. So if you consider that if wave packet is correspond to a single point, okay, then what happens? Motion of a point we can explain by classical mechanics. That means Newton's law of motion. So what happens if you have to consider the wave packet corresponding to a single point? Then our quantum mechanics relation should convert into the Newton's law of motion. That is your Ehrenfest theorem. So that means if we have to take the average measurement of a physical quantity. Average measurement means if I have to take average measurement of a position, that is known as the expectation value of a position, and differentiation it with respect to the time, that is dx by dt, that should be equals to the expectation value of momentum divided by mass. That means this relation will equals to the momentum is equals to mass into the dx by dt. Okay, so this is your Newton's second law of motion. Momentum is equals to mass into the acceleration. So that means we have to find out the average or expectation value of the position. Then I have to differentiate it with respect to the time. This value should equals to the expectation value of momentum divided by mass. That I have to find out. This is the first part of Ehrenfest theorem and this is the second part. Second part means force is equals to the rate of change of momentum. So actually it is a classical mechanics, but I have to derive this relation by taking expectation value. And expectation value is a quantum mechanical concept. So I have to take the average measurement of any quantity, and this average measurement corresponding to a point, and that point is a point means classical mechanics. So that is quantum mechanics approaches to the classical mechanics. Okay, so this is about your Ehrenfest theorem, and what I have to prove is that first of all I have to prove that dx by dt should equals to the momentum divided by mass, and in second part rate of change of momentum or differentiation of time with respect to time of expectation value of momentum should equals to the differentiation of a potential and their expectation value. So in today's lecture we are going to derive the first part only. Okay, so what is the Ehrenfest theorem? Ehrenfest theorem, that is it gives the correlation between classical mechanics and quantum mechanics when wave packet reduces to the point. Okay, so from this what I have to do is I have to use quantum mechanical concept, then from that quantum mechanics I have to come to the classical mechanics. Okay, so I have to derive the Newton's law of motion from the by taking expectation value. So what is the first I have to prove is that differentiation of expectation value. Okay, differentiation of expectation value of position coordinate, that should be equals to the expectation value of momentum divided by mass. Okay, that is the first part of Ehrenfest theorem that I have to prove. So let's start. Now, what is the expectation value of a position coordinate? Here we will take expectation value of a position. Okay, how to write the expectation value of a position coordinate? It will be written as integration from minus infinity to plus infinity. First we will take psi star, then that is the position coordinate, okay, into psi into dx, where psi is a normalized wave function. Okay, it is a normalized wave function. Why it is known as normalized wave function? If it is not normalized, then in denominator I have to write integration from minus infinity to plus infinity psi star psi into dx. But it is normalized means this value should equals to 1. Okay, you know about this condition. So this is the expectation value of a position coordinate. Now I have to differentiate it with respect to the time. So expectation value of this, so this will be equals to the d dt of, okay, here I have to take partial differentiation because psi is a function of two variable x and t. Okay, so d dt of, now integrate this minus infinity to plus infinity psi star x psi into dx. Okay, so now this can be written as, if you write this will be infinity to plus infinity. I can write this expression as a x, this will be equals to d psi star by dt into x psi, okay, plus second term will be your x psi, x psi star into the psi star into the x into d psi by dt, okay, into dx. So here what I have to do is I have to differentiate with respect to the time. So this is the first term is d psi star by dt, and this second here it is d psi by dt. So I have to substitute these values of d psi star by dt and d psi by dt from Schrödinger's equation. Okay, so what is Schrödinger's equation? Schrödinger's equation is IH cross d psi by dt is equals to the, it is minus h cross square divided by twice m del square psi divided by dx square plus potential, okay, v psi. Okay, so it is one dimensional because it is dx square, okay, d square by dx square. So from this equation, this h cross will get cancelled, I will be goes to this side. So this equation will gives you d psi by dt is equals to, this will be equals to your, if you take I this side and multiply I to the numerator and denominator, this equation will be converted into IH cross divided by twice m del square psi divided by dx square plus v divided by IH cross into psi. Okay, so this is your first equation. Here it is minus sign. If you take IH cross here divided by this IH cross, okay, and multiply I here, it will be minus 1 minus minus plus, so this will be equals to your IH cross. Okay, so from this equation you will find out the value of d psi star by dt taking complex conjugate of it. Okay, so this I will be now minus IH cross divided by twice m del square psi divided by dx square. This will be also minus v divided by IH cross into psi star. Here also it will be psi star. So we have taken complex conjugate of this equation. So this is suppose your equation number 1. This is your equation number 2. This is your equation number 3. Okay. And how this equation comes from Schrödinger's time dependent equation. Okay, if you substitute these values in this equation, what we will get? We will get the equation like this. The equation will be, this will be equals to your d dt of expectation value differentiation is equals to integration from minus infinity to plus infinity. Substitute this value here. This will be minus IH cross divided by twice m del square psi star divided by dx square plus into this x psi, okay, and second term will be your minus v divided by IH cross psi star, this is the value of this, into this x into psi Okay, this is the first term plus, now I have to substitute this. Okay, plus psi star into x into, what is the value of d psi by dt in this equation? This will be I h cross divided by twice m d square psi divided by dx square plus that quantity plus, here first take this quantity psi star x into the v divided by I h cross into psi. Okay, so these two quantities are same. Okay, so these two quantities will get cancelled, and what is remaining is this into dx. Okay, because I have to take the integration of this. So now we have substituted these values. These two quantities are same, so it will get cancelled. So this will be gives you d dt of expectation value differentiation is equals to, here both I h cross divided by twice m is common, take outside, and integration from minus infinity to plus infinity. This will be gives you, this will be minus quantity and this will be positive quantity. So we will take first this quantity. This will be psi star x into d square psi divided by dx square. Okay, and minus this quantity will be, you will take first this quantity x into psi d square psi star divided by dx square. Okay, and its integration is from minus infinity to the plus infinity. So this is your expectation value, that differentiation of expectation value with respect to the time. So from this, now in this equation